This is outcome 30, and we're going to talk about why KW equal Ka times Kb. Okay, so if I have a weak acid, any weak acid, HF, for example, plus H2O, and I get in equilibrium H3O plus F minus. And the Ka for this is the concentration of H3O plus times the concentration of F minus divided by the concentration of HF times the concentration of H2O, which is 1. Okay? So now the conjugate base also exists. So if I'm looking at this acid-base system, F minus, if I had a solution of sodium fluoride, NaF would go to Na plus F minus. This is a weakly basic salt. Then the F minus plus H2O would react to give HF plus OH minus. And that's acting as a B. So for this conjugate base of HF, F minus, the Kb, it's the basic dissociation constant, is the concentration of HF times the concentration of OH minus divided by the concentration of F minus divided by the concentration of H2O, which is equal to 1. One more thing to do. So I need these two equations here. Okay? And we've already discussed the water reaction. H2O plus H2O gives us H3O plus O minus, OH minus, and Kw for this is equal to the concentration of H3O plus times the concentration of OH minus divided by the concentration of H2O squared, which is really 1. Okay? Because it's really activity. So now if I go from our thing, we know the equation Kw. I told you that Kw is equal to Ka times Kb. So if I come up here and I say Kw equal Ka times Kb, then I can plug in for Ka, which is a concentration, this equation up here, the concentration of H3O plus times the concentration of F minus divided by the concentration of HF, and times Kb, which is the concentration of HF, times the concentration of OH minus divided by the concentration of F minus from this equation right here. So when I multiply those, my F minuses cancel, my HF cancels, and I get equal the H3O times the concentration of OH minus. And that's why that works. So that's where that's coming from. It's just a manipulation of all these reactions.